Right after.
All right, no problem.
Good afternoon, ladies and gentlemen.
Good afternoon.
We're Team 3D Solar. Our project is the three-dimensional solar panel. My name is Carl Jai. These are my team member Christian Bernard and Mohammed Arif. Now, for a quick introduction into solar panels, solar cell research and development has been around for many years, since the early 1800s. And as of recent times, they have become very popular as a growing demand for energy generation. Okay, basically a solar cell, or as we know it also as a photovoltaic cell, what it does is it converts sunlight into electricity by photoelectric effect. Now this effect will be explained throughout the presentation. Now solar cells, as we see here at the bottom left of the picture, can be electrically connected to form what we know a module, as we see in the middle. And modules can be wired together to form an array. This will produce the maximum amount of energy generation. Now modern solar cells, as we know them today, were developed back in the 1950s by a company called Bell Laboratories. And the first application of these modern cells can be seen on a satellite that was launched in 1958 called Vanguard 1. Now for our panel statement, what we want to do is address the effect of pollution by reducing the overall carbon footprint. Now, by implementing our 3D geometry for our solar panel, we expect to increase energy generation, and hopefully these can replace polluting fossil fuel plants. Also for our design, we want to create stationary, meaning that it's going to be in the absence of a solar tracker. It's going to be easier for installation and thus reduce the cost associated with this. Now, our motivation is very simple. We want, first of all, on the top of our list is reducing the dependence on fossil fuels. As we know, electricity demands increase daily, and fossil fuels such as oil and gas will become scarce. It's for this reason that we want to introduce our 3D design to harvest as much sun energy as we possibly can, for the sun's energy is an unlimited resource. Now, hopefully by doing that, we can also reduce the electricity costs associated with that and reach remote areas by making it portable. Now for our objective, we want to maximize the sunlight absorption, store all this energy that we've absorbed, effectively utilize this energy, and hopefully introduce this into residential areas.
Globally, as we know, the energy demand has increased, and to overcome that energy, this is pushing us towards more and more clean energy sources. And solar panel is a good alternative to fossil fuel energy creation. And in 2005, it was a $38 billion industry, and it's rapidly growing at 10% a year. It's more implemented in developing countries, such as in countries in Asia and Africa. More and more villages have been installed with solar panels to overcome their basic electricity needs. Our design goals are to create a 3D shape which can be compared with the flat surface solar panels with the same base area, and get the maximum absorption out of that 3D shape. And we're considering two different materials, monocrystalline and polycrystalline. Monocrystalline silicon cell is in pure form, and it's expensive but it's efficient. And what we're looking into polycrystalline, which is cheaper, and as we said, we will be utilizing the 3D geometry, and it will increase the efficiency. These are the basic shapes that we see every day, conventional rectangular shape. And these are our initial designs. And we're trying to have the same base area in our 3D shape design to maximize our energy.
Alright, so how it works. This is a photovoltaic cell. These cells are made of silicon and made of at least two layers, a positive and a negative, or P-type and N-type. And how it works is when the sunlight is absorbed, it absorbs the photons and electrons are released into the circuit. Since silicon is a semiconductor of electricity, it efficiently transports the current through the cell, and this circuit, it captures the flow of electrons and so the solar panel is where that process takes place. So when the current then moves to the charge controller, which regulates the amount of current that goes to the battery to prevent overpowering of the battery, which causes permanent damage. DC power can be used from the battery, but since most appliances are AC power, we use the inverter to convert it. The test will be placing it outdoors for a full day, along with a rectangular panel of the same surface area, and the data will be recorded and compared to prove our efficiency. This is the cost analysis. As you can see, the inverter is most of the cost, which is about $1,200. The charge controller is about $200. Everything else is roughly $100, for a total of $2,000.
This is our timeline. As you can see here for the fall, this is what we've completed, and this is what's expected for the next semester. Our conclusions: we want to increase sunlight absorption and efficiency, promote the use of clean unlimited energy, and design an affordable and convenient product. These are references where we got some of our pictures from and information. Thank you.
Okay. Timing was not good.
Yeah.
Yeah. You are 45 seconds late, and then the first student spoke half of the time, 2.5 minutes. Now, you need to be careful.
So you can adjust that.
Yes.
Scroll through to the end there and back. Go to the end slide and then back up. One more. Okay, that one. So all the green is completed.
All the green is what we've done this semester so far.
This is type on November.
Excuse me?
November.
Oh,
So you don't plan on doing your testing until the last 2 months?
yeah, like once we're sure we've made what we're planning on doing.
So no intermediate testing, so if you need to do some...
What about
Yeah,
revisions?
like this timeline is very preliminary because we can't really see in the future, but it can change.
We're going to begin
It might be a good idea to be realistic that at some intermediate point, you're gonna do some preliminary testing just to fine tune what the final end product is gonna be.
Okay.
So when that final testing comes up in March, you wanna put the year as well. When that final testing comes up in March 2014, that you're not gonna get any major surprises that will cause you to have to redesign everything that you've done. You follow what I'm saying?
I understand.
Okay.
So do you want us to put the year in there as well?
Put the year, so you're gonna have fall 2013,
Okay.
spring 2014, and maybe in January somewhere, I'd put one block of preliminary testing.
That's what we plan on starting the construction of the actual preliminary design in January when the semester begins.
So then towards the end of January, you should be able to do some preliminary
Hopefully,
testing,
yeah.
something like that.
Okay.
And it would make it a little bit more real, because please know from experience that when you get to that final testing, there are gonna be challenges that you're gonna have to deal with.
Yeah.
And some of those challenges could drive you back to a redesign, which you're not gonna have time to do, so you wanna be proactive on that.
Any other
Any further
questions?
questions?
What is the purpose of the simulation in your project?
This one here?
No, there's a simulation line
Simulation.
item you had in the schedule before testing, I believe.
Timeline.
Oh, what we wanted to do is basically kind of run like a heat transfer analysis on the panel, like see the heat radiation that we can induce on the panels and
Go back to
once we know.
go back to that slide. You may want to relabel that line item then.
So once you do the simulation, what is the outcome?
Like we want to check out our materials just to make sure that they withstand, being in the open for how many days, months, years, that it withstands weather, that we choose the right type of material.
But you're not designing you're not finalizing your design based on your simulation?
Yeah, well, we designed the prototype in SolidWorks, running a heat transfer simulation, like a radiation simulation, just to get like an average or estimate result from it, and we're gonna go from there with our prototype and see how it compares to the actual testing.
And we do plan on using some specific photovoltaic software but we're kind of working with the company to kind of get our hands on such a software.
So that slide shows that you've done some simulation already. What have you done?
Very basic in SolidWorks. We have tried, but SolidWorks is more like a radiation heat transfer type concept, and not really photovoltaic based simulations.
So you need some proprietary software or
Yeah,
something?
Exactly. So we've gone to companies maybe so we can get like a trial or something to use their software and maybe run some tests on it.
And what response are you getting on that?
Well, there are some trials available. It's only for about 7 days. We do not know if that will be enough to do our complete testing, so we're trying to.
We want to make sure we have all our information first before we take the trial to do our test.
You may want to find a creative way of combining testing and simulation, because it is one and the same based on what you're saying. And some of the things that I spoke to you about, having a pre-test before your final test, is actually what you're calling simulation. So find a way to combine those two, because it is in effect what you're saying.
Testing and simulation.
Right.
So testing and final testing.
Or testing slash simulation, or
Testing
simulation slash testing, something
Okay.
like that.
You can report deadlines from the slide.
Yeah.
Oh, delete them?
Yeah,
Okay.
that will be great.
All right.
Other questions? Other questions?
Cool.
So,
Yes.
Are you going to use any optimization to come up with your final design, or it's just gonna be based on the trial and error to see which shape configuration works better?
To optimize. Right.
It's kind of a trial and error process, but we're limiting because there are many shapes that
Yeah,
you
that's
can
the
use,
question.
infinitely many. But we're reducing it down realistically what we can achieve into basically the pyramid that you just saw, and maybe the cube. We've been thinking about another shape, but we don't want to put it in here as of yet because we're not too sure on that.
Or any concave shapes, you know?
We have thought
Yeah.
about a dome shape, maybe parabolic, but for now we're mainly focusing on the pyramid.
Any parabolic or dome shape will change the material as well. Then you have to consider a thin film material.
Yeah.
That won't be.
Maybe you could consider them in the simulation
It's
to
a
see
possibility.
what's gonna be, not necessarily in the construction.
But so far for us, the pyramid has been the most convenient for design, simulation, and for actual construction to put it together. The pyramid will be
Okay.
the best option for us. But we are still looking at a dome and also an inverse dome.
So eventually you're gonna justify your pick of the configuration based
Yeah.
on your results.
The simulation and the testing.
Yeah.
So hopefully so far SolidWorks has proven to you that 3D solar panel is a lot more efficient than 2D.
Yes.
Yes?
Yes.
Yes.
Unequivocally?
Well, not really. SolidWorks proves it does, but we just know from
An estimate.
maximum absorption occurs at 90 degrees at perpendicular to sunlight. So, the sun is always moving and the rectangular panel is just here. So if the sun moves like this, you're going to get maximum absorption from surfaces that are always exposed. So that's our theory behind it so far.
You may want to argue that theory earlier on in your objectives or in your statement of problem, because that may be a point that unless someone is into heat transfer and those kinds of things, they may not get it. You follow what I'm saying?
Yeah, you understand?
Did you do any cost analysis?
Yes, we.
Yeah.
100%.
Yeah.
Wow.
Yes, 2000.
Yeah.
Okay. Did you do any, like if you are trying to do a mass production?
Mass production?
Yeah.
As of now, no. We're first
So you
trying to
didn't do any
prove
cost
it to be
analysis for
successful.
mass? Okay.
Okay.
Yeah.
Do you have any other questions?
No.
Thank you very much.